These are the notes for AP Calculus on the topic of relative, also called local extrema, and increasing and decreasing intervals using the first derivative test. So first, let's take a look at what relative or local extrema refer to. So extrema, just think of that means like the extreme values, and that refers to both maximums and minimums of a function. And relative and local are just two different words for the same thing in terms of maximums and minimums. It just means relative or nearby or locally. A relative maximum is a point like right like this, where it's above the points on either side of it. And here's another relative local maximum right here, and another one right here on this graph. So when you have the graph, it's easy to identify them. They're like the top of a hill. However, we're not going to always have the graph. Sometimes we'll have the equation, and that's where our first derivative comes into play. So notice right here, the first derivative, which represents the slope of the tangent line, is positive. So we can say f prime is positive until we get right here where it levels off. The slope is 0, and then the slope is negative afterwards. And what that shows us with the original function is when the slope is positive, that means the original function is increasing. And then after 0, then it's decreasing. Same thing on this one, it's increasing and then decreasing. Slope is positive and then negative, increasing and decreasing. So on this first one, it levels off and the slope is 0, but notice on this next one, we've got a cusp, an abrupt change in the slope, so the first derivative doesn't exist, but it's still a relative or local maximum. And right here, we've got a corner. So the first derivative doesn't exist, but it's still a local maximum. Now let's look at what relative and local minimums refer to. So the relative or local minimums, that's when it's like the bottom of a valley here. So you can see we've got a relative local minimum right here on this graph, right here on this graph, and right here on this graph. So notice what's happening with those is the first derivative is negative, the slope is negative. Right there, and then it's 0, it levels off right there, and then it's positive. On this one, still the slope of the tangent line is negative, and then it doesn't exist there because of the cusp, and then it's positive. And the slope, the first derivative is negative, a corner there, so the first derivative doesn't exist, and then positive. So again, this shows us when the first derivative is negative. When the slope is negative, that means the original function moving from left to right is decreasing. And when the slope or derivative is positive, that means the function is increasing. So notice all the places we have relative minimums and relative maximums, they have something in common. The first derivative either is 0 or it does not exist. So that's what critical numbers are. Critical in this case meaning important. Sometimes they're called critical points, sometimes critical numbers. Same thing. It's where the derivative of the function is either 0 or undefined. And the undefined, that'll show us that the derivative does not exist. These are the places that relative or local extrema could occur. It doesn't guarantee you're going to have them there, but these are the only places they might be. So here it says, find the x-coordinate or coordinates of all the critical points of the function. So we do that by finding the first derivative. So here, since they're added and subtracted, we can take the derivative of each term separately. So f prime of x would be, using the power rule, 4x cubed plus 12x squared plus 8x. Notice this one, there's no denominator, so we don't have to worry about it being non-existent or undefined. And there's no even roots either. So we can just see what makes this equal to 0. And you can first factor out a GCF of 4x. And that'll leave us with x squared plus 3x plus 2. And then we can factor this trinomial further. Factors of 2 that add up to be 3 would be 2 and 1. And since the leading coefficient's 1, we can use the shortcut and just jump to x plus 2 and x plus 1. So since it's equal to 0 and it's in factored form, the only way it can be 0 is if one of these is 0. So if we set 4x equal to 0, we get x equals 0. you set x plus 2 equal to 0, subtract the 2, you get x equals negative 2. And if you set x plus 1 equal to 0, you get x equals negative 1. So these are our three critical numbers, the three x values where we might have a local min or max. Let's take a look at one more of these. On this one, that's a little more complicated. I'm going to first rewrite the square root of x. So it's easier to find the derivative with a fractional exponent. That's the same as x to the 1/2 power. And then we've got 2x minus 4 to the 4th power. So now when we find the derivative here, f prime of x, since they're multiplied together, when they're adding and subtracting, you can take the derivative of each one separately, like the next one. When they're multiplied together and they both have variables, in this case they both have x's, that's where you have to use the product rule overall. And notice we'll also need, because this one has a function inside of 2x minus 4, when we take the derivative of this one, we'll need the chain rule right there. So let's start with a pattern for the product rule. So remember, with the product rule, you take the derivative of the first one, then use the power on x to the 1/2. That's 1/2 x to the negative 1/2. Then times the second one as it is, so we leave it 2x minus 4 to the 4th. And then plus, then we have the first one as it is, so we just leave it as x to the 1/2. And then we take the derivative of the second one, and that's where we'll need both the power and chain rule. So first using the power rule on the outside, times 4, and then the function side stays the same whenever using the chain rule. So it stays 2x minus 4, and we subtract 1 from the exponent, so that gives you to the 3rd. And then using the chain rule, it says we have to multiply by the derivative of the inside. So the derivative of 2x minus 4 is 2. So then we can simplify it from there by, again, factoring. This one's a little more advanced factoring, but we're still going to factor. Just like on this one, we took out a GCF of 4x. That's what we're going to log for first. So here's our first term, all multiplied together, plus here's the second term, all multiplied together. So the GCF, what those have in common, the first thing you might notice, they both have 2x minus 4. This one has it to the 4th power, to the 3rd power. So we take it out to the lower exponent, which is 3. So we take out 2x minus 4 cubed as part of our GCF. And there's one more thing, too, that's a little more complicated. We've got x to the negative 1/2 and x to the 1/2. So we take out x, and just like we did with the 3, we're going to take it out to the lower exponent. In this case, the lower exponent is a negative 1/2. So that same rule works even when you have fractional or negative exponents. And now, whenever you take out a GCF, you have to put what's left of each term. So what's left of the first term, we still have the 1/2. This x to the negative 1/2, we completely factored out. And then we had 2x minus 4 to the 4th. We took out 3 of them, so there's one more left. So we still have 2x minus 4, but now just to the 1st power. Because remember, the way you figure out the power that's left, is when you multiply these, distribute it back out, you add the exponents with the column base. So 3 plus 1 does give you back 4. Because we're going to use that same property on the next term. So we have the plus sign next. Now we have to put what's left of this one. So we have 4 times 2. That's 8. This is completely gone because we factored it out to the 3rd power, and that's what we had. And the only question is what's left of this x. It was to the 1/2. We factored it out to the negative 1/2. So using the same property, just like the 3 plus 1 has to add before, this negative 1/2 we factored out, plus this exponent that we're trying to figure out, has to give you back, the 1/2, the positive 1/2 there. So in this case, it'd have to be negative 1/2 plus 2/2. The 2/2 is the same as 1. And it usually, not always, but it usually does work out to be an integer like 1 or 2 there. So, all right, now we can keep simplifying it. We're simplifying it so it's easier to determine the critical numbers, the thing that makes the derivative, the x values that make the derivative 0 or undefined. So now that we've taken this out to the negative 1/2, we can move it to the denominator, since it's factored out, and put it in radical form. So in radical form, that will be the square root of x. And we still have this 2x minus 4 cubed. And then we usually have some simplifying to do with what's left after taking out the GCF. Not always, but a lot of times there is. So to simplify that, first we can distribute out the 1/2 times both of these. 1/2 times 2x, the 2's cancel out, we just get x. 1/2 times negative 4 is negative 2. We still have the plus sign. And we still have the 8x. Okay. And we've almost got it here, just a little more simplifying to do. So this 2x minus 4 cubed, we could leave like that. That's perfectly fine. But you might notice there's a GCF here. How it's a little different how we factor it if we choose to take out the GCF because of the exponent there. Common mistake students will make is they'll take out the 2 and leave it 2x minus 2 cubed, but that's not correct. So the way to see how it's going to work here is we basically, I'll just write off to the side so you can see if you do want to factor out a 2. We've got 2x minus 4 times another 2x minus 4 times another 2x minus 4. Because it's cubed, right? I got 3 of them. And each one of them, we're able to take out a GCF of 2. So this would be 2x minus 2. This one we can take out a 2. Be left with x minus 2. And this one we take out a 2. So what you're really doing is not taking out 1 2, you're taking out 3 2's because it's cubed. So then you can multiply those together. 2 times 2 times 2 gives you 8. And then what's left is x minus 2 to the third power. And then right here, notice we've got some like terms here. 8x plus x is 9x. And then we still have minus 2 over the square root of x. So now we've got it simplified in factored form. Now we can find our critical numbers. And critical numbers are where the derivative is 0 or undefined. So 0, that comes from the numerator. So when you set that equal to 0, one of those factors would have to be 0. Notice the 8 is just a constant. Unlike the 4x, there's no variable, so the 8 can never be 0. If you set x minus 2 equal to 0, don't worry about the cubed right now. As long as this is 0, cubing 0 is still going to be 0. That will give us x equals 2 as one of our critical numbers. And if we set 9x minus 2 equal to 0, you'd add the 2 divided by 9, so we get x equals 2/9. So those are the two critical numbers that make the derivative 0. But unlike the first one we did, this one actually does have a denominator. So when you set that denominator equal to 0 to see what makes it undefined, notice whatever's inside, the square root of 0 is 0. So in this case, if you set that x equal to 0, we get x equals 0. So that critical number makes the derivative undefined. So these are the only 3 x values where we might have a critical, well, there are critical numbers where we might have a relative minimum or a relative maximum. All right, now let's see that we've looked at finding critical numbers, how we can use those with the first derivative test. So it's called the first derivative test because that's what we're using. So what we're going to be doing with the first derivative test is testing the intervals between the critical numbers to determine if the first derivative is positive or negative. So let's look back at our graphs we did. Notice whenever the first derivative was positive, that corresponded to when the function was increasing, because the first derivative is the slope. If the slope is positive, you're going to have an increasing function. So f of x is going to be increasing whenever the first derivative is positive or greater than 0. Similarly, the original function, whenever it was negative, that's when the original function was decreasing. Because again, if you have a negative slope, that means from left to right the function is decreasing. So f of x is going to be decreasing whenever the first derivative is less than 0. And then if we look back here to find the, after we test to see in between the critical numbers, if its first derivative is positive or negative, then if the derivative, let's look at what happened on these first ones here. Notice everywhere here, moving from left to right, the derivative changed from positive to negative, from increasing to decreasing. That means we've got a relative or local maximum. again, these are just the two words for the same thing. Relative or local maximum. And notice whenever the first derivative changed from negative to positive, that indicated we had a relative or local minimum. Assuming the function's continuous there. So that's going to be the case unless you have something where there's like a vertical asymptote or a hole where the function's not even connected there. But as long as it's continuous there, that's going to indicate that. All right, so now let's take a look at some examples here. So these say to find the increasing and state the increasing and decreasing intervals of the function, and then find the x coordinates of all the relative extrema. That refers to both minimums and maximums, and identify each as a relative maximum or a relative minimum. All right, so first thing we need is called the first derivative test, because that's what we're going to use for all this, is to find the first derivative. So let's find f prime of x. And again, this one, terms are just added and subtracted. So we can just take the derivative of each one separately. Derivative x to the fourth using the power rule. Bring down the 4, reduce the exponent by 1, so 4x cubed. Minus, bring down the 2 times 8 gives you 16, reduce the exponent by 1, just x. And remember, the derivative of a constant by itself is just 0. So there's our first derivative. And then we just, in this case, there's no denominator or negative exponent, so we don't have to worry about the undefined case, just what makes it 0. And you can factor out a GCF of 4x here. And that'll leave us with x squared minus 4. And notice that factors a little further. We've got 4x. And using difference of perfect squares factoring, that factors into x plus 2 and x minus 2. So we've got 3 factors here. And one of these has to be 0. So if you set 4x equal to 0, you get x equals 0. If you set x plus 2 equal to 0, you get x equals negative 2. If you set x minus 2 equal to 0, you get x equals 2. So those are our 3 critical numbers, but now we're not going to just stop there. To figure out all this information, both the increasing, decreasing intervals and the to determine the relative mins and maxes, we're going to put this all on the number line, all our critical numbers. And the first thing to do is label your number line, okay? So I'm going to label it f prime of x. This will remind you what you're testing it. And only put the critical numbers on the number line. Don't put any other numbers on there. So just put negative 2, 0, and 2. And put them above the number line, because below we need space to put what's the first derivative. So notice all 3 of these values made the first derivative equal to 0. And then, here's how the first derivative test works. We just have to test in between these critical numbers to see if the first derivative is positive or negative. And you can technically test in any form of the first derivative. These are 3 different forms of it. But usually the factor form is going to be the easiest to test into. So let's test in there. And remember, we don't need the exact value. All we need to know is if it's positive or negative. So if we put in negative 3, something less than negative 2, like negative 3, 4 times negative 3 is negative. Negative 3 plus 2, negative. Negative 3 minus 2, negative. Take 3 negative numbers, multiply together. It's an odd number of negatives. That's going to be negative. So we know everything on this interval is negative. Between negative 2 and 0, you could test negative 1. 4 times negative 1 is negative. Negative 1 plus 2 is positive. Negative 1 minus 2 is negative. 2 negative times a positive, the negatives cancel out, so that's going to be positive. Between 0 and 2, you could test 1. 4 times 1 is positive. 1 plus 2 is positive. 1 minus 2 is negative. 2 positive times a negative is negative. Here you can test 3. 4 times 3 is positive. 3 plus 2 is positive. 3 minus 2 is positive. 3 positive numbers together is positive. So you will see this alternating pattern quite a bit, but it's not always going to alternate like that. So that's why we have to test everyone, because it doesn't always do that, even though it happens a lot. So then what this tells us about our original function f of x, remember whenever the first derivative is negative, we know the original function is decreasing because it's whenever the first derivative is positive, the original function is increasing. Then back to negative, decreasing, back to positive, increasing. So that allows us to state the increasing, decreasing intervals. So now we can say f, or f of x, you could read it either way, is increasing. You can start with either one. On -2 to 0. It's easiest to use interval notation here. And also u from 2 to infinity. And then we can say f is decreasing. On -infinity to -2. And from 0 to 2. You say on when you're talking about intervals. If you say at, then it sounds like you're talking about points, and this could look like a point. So one other thing what other way you could write with intervals here? Not everybody agrees on whether these, on the ones that aren't infinity, should be parentheses or brackets. And in textbooks and in the AP test, you could see it written both ways. So you could put brackets on these, everything except for the infinity. You never put brackets on because it's not a specific number, and that would still be correct. So either way, some people think it should be included. Some people think it shouldn't. I don't include it when I write it because to me it makes more sense that it's 0 there, so it's not technically increasing or decreasing. So I don't include it on either one, but sometimes people would include it on both on those. So just keep that in mind that either way is correct. All right, and then this also shows us where we have our relative minimums and maximums at the critical numbers. So if we take a look at each one of them, notice here, it goes from decreasing to increasing. The first derivative changes from negative to positive. So remember we said that whenever it changes from negative to positive, it's a relative or local minimum. So that's a relative minimum right there. And at 0, it changes from positive to negative. It goes increasing to decreasing. So that's a relative or local maximum. And when I say from positive, I'm always moving from left to right, just like we read. And another one where it changes from negative to positive, decreasing to increasing, so that's a relative minimum. So in this case, we have 2 relative minimums and 1 relative maximum. So we can say f has relative minimums at x equals -2 and x equals 2. Or in this case, you could say plus or minus 2 since they're just the opposite of each other. And f has a relative maximum at x equals 0. Notice here, because rel min and rel max, those are, and DEC and INC, those are not official abbreviations. So when you write an answer, write it out, the words. Those are just my shorthand because it's a lot to write down, so our number doesn't get too crowded in there. So these are the increase and decrease intervals and the relative x coordinates of the relative min and maxes. Now, usually that's all they ask for is the x coordinates of the relative mins and maxes. Once in a while, you might have them ask for both coordinates. And to find the y coordinates, all you'd have to do is plug these x coordinates back in the original equation to find their corresponding y coordinates if you do need them. But they don't ask that very often because the AP test is a time test, and that's just one more thing that's a little time consuming to find. So usually they'll only ask for the x coordinates. All right, let's take a look at the next one here. So the next one's a little more complicated, so let's first rewrite this one with fractional exponents. It's in radical form. So this is the same as, instead of the cube root of x to the 4th, that's x to the 4/3. And then plus 4, instead of the cube root of x, x to the 1/3. Now let's go ahead and take the derivative using the power on each of these since they're separated by a plus sign. So g prime of x, using the power, would be 4/3. X subtract 3/3 from that one to the 1/3. Plus 1/3 times 4 is 4/3. X subtract 3/3 from that gives you -2/3. And again, to simplify it, let's try factoring. So let's look for the GCF here. So the GCF of our two terms, notice they both have a 4/3, so we can take that out. And we can take out x to the lower exponent is negative 2/3. All right, let's see what we have left now. So the 4/3 is gone. This was x to the 1/3. And we took out negative 2/3. So again, negative 2/3 plus what would give you 1/3? That'd be 3/3, which is just 1. So just x to the first. And then plus. Now we factor this entire thing out, 4/3 and x to negative 2/3. So sometimes students think there shouldn't be anything there. But to hold the place, when you factor everything out, you still need a 1. That way, if you distribute it back out, you get this times 1 would give you this back. So don't forget the 1 there if you factor everything out of the term. And then we can just simplify it. So now this 3 is already on the denominator from the 4/3. And if we put this in radical form, that'd be the cube root of x squared. Since it's a negative exponent, it goes on the denominator. We still have the 4 here, and in this case, it's already simplified. It's just x plus 1. So now we've got it as a single fraction, so now we can just set both the numerator and denominator equal to 0 to find all our critical numbers. So let's start with the numerator. 4 will never be 0, so you just set x plus 1 equals 0, you get x equals negative 1. That makes the derivative 0. And notice the 3 will never be 0, and just set what's inside the radical equal to 0 would give you x equals 0. So in this case, we only have 2 critical numbers, so now let's put those on the number line. Again, always label your number line, because later on we're not always going to be only testing the first derivative. So it's important. Start getting a good habit right now of always labeling your number line. So you'll remember what you're testing in. In this case, it's g prime of x. And in this case, we only put on our 2 critical numbers above the number line, are negative 1 and 0. But in this case, at negative 1, that makes the derivative 0 because it makes the numerator 0. But 0 came from the denominator, that makes the derivative undefined. And that distinction sometimes makes a difference, as we'll see on this one. So let's test. And here we have to test in the derivatives. It's going to be easier to test in this than the original form or even this factored form. So let's test in the numerator first. So here we could test something less than negative 1, like negative 2. Well, negative 2, the 4 is always positive, plus 1 is negative on the numerator. Normally I would test it in the denominator also. Notice it's not going to be imaginary here because it's an odd root, which is okay. But there's a shortcut you can use here because notice this is squared, which means if it's an even exponent there, it's never going to be negative. So we don't have to worry about the denominator sign ever being negative, so we can really just test the numerator. So negative 2 makes the numerator negative. So it's going to be a negative here. Here you could test negative 1/2. Plus 1 is going to be positive. Again, we don't have to worry about the squared there. That's never negative. So that's going to be positive there. And then if you test positive 1, something greater than 0, 1 plus 1 is positive. So it stays positive there. So this shows us that the original function g of x, when the first derivative is negative, would be decreasing, positive increasing, and still positive increasing. So we can write down our increasing, decreasing intervals first. So we can say g is increasing on negative 1. Now here's where it matters if it's 0 or undefined. If this was 0, we actually would not have to stop our interval. We could go all the way to infinity. But since it's undefined, you always have to stop your intervals, even if the sign doesn't change. So we do have to stop at 0 here, and then go from 0 to infinity. And then we can say g is decreasing on negative infinity to negative 1. In this case, there's only one interval. And let's see at our 2 critical numbers if there's a relative min, relative max, or neither. So negative 1, notice it goes decreasing to increasing. So that's a relative minimum. The first derivative changes from negative to positive. And at 0, notice the This derivative g prime does not change sign. So because it doesn't switch sign, it's neither. It's not a min or a max. So we just have a relative minimum and no relative maximums. So we can just say g has a relative minimum at x equals -1. If you want, you can say it has no relative maximums, but it's really not necessary. You just have to state what is there. You don't have to state what's not there. All right. Now let's take a look at another one here. So here when we take the derivative, we'll just have to use the chain rule along with our power rule. So it would be h prime of x equals, use the power rule first, so that'd be 3, the function side stays the same, 2x minus 3, reduce the exponent by 1 squared, and then using the chain rule times the derivative inside is 3. And then this one, notice there's no negative exponents or denominators, so we just set it equal to 0, and then you can multiply, sorry, not a 3, the derivative inside is 2, my bad. Of 2x is 2. So then you can multiply the 2 times the 3 gives you 6. And then 2x minus 3 squared. So this one, notice, is already in factored form. 6 times 2x minus 3 squared. So there's no need to factor because it already is. So 6 will never equal 0. If you set 2x minus 3 equal to 0, you get x equals 3/2. So here we only have one critical number. So let's just put that one on the number line. And again, we can label it h prime of x. And we can put 3/2 on our number line, or one critical number. Now, and that's what makes the derivative 0. And then you could test something less than 3/2, like 1 or 0. Or, notice in this case, we've got another even exponent. So this can never be negative, no matter what we test in here. That 6 is positive. So, because of that, we know it's going to be positive here. The only place it's 0 is right at 3/2. Everywhere else is positive. It'll be positive here and positive here. Which shows us that h of x is increasing and still increasing. So we can say h is increasing on, notice, remember on the last one, because it was undefined, the derivative, we had to stop there when we wrote these increasing intervals, even though it stayed increasing. Here, though, we don't have to because it's 0. We can keep going. So you could stop, but you just don't have to. You can say it's increasing on negative infinity to infinity, basically everywhere. Okay. And notice at 3/2, we don't have a relative min or max because the first derivative doesn't change sign at all. What this would look like, if you're looking at it, levels off for a little bit there. It basically goes increasing, that levels off for just an instant, the slope is 0, and then it's back to increasing, kind of like the cubic graphs. So that's why you can say it's increasing the whole way. And you could say it has no relative extrema if you want, or just state where it's increasing. That's fine. Either way, I'll just put h has no relative extrema. Remember, extrema refers to both minimums and maximums. And what this type of function is called when it's always increasing or always decreasing, we'll see this term later on, it's referred to as strictly monotonic. Just think mono means one, right? So it's going one direction, either always increasing or always decreasing. In this case, it's always increasing. So just some terminology we'll see later on, just your first introduction to a strictly monotonic. The function is always increasing, or it would also be strictly monotonic if the derivative was all negative here, it was always decreasing, it would also be strictly monotonic. All right, now let's take a look at some with some slightly different instructions. Sometimes they may not ask you about the to write down the increase and decrease intervals. And they might only focus on the local mins and maxes, which are the same as relative mins and maxes. So we're just trying to find the x-coordinate of each local minimum and local maximum. But what they'll do with that is, on free response, sometimes they'll ask you to justify your answer. How do we know it's a local min or a local max? So let's figure this out. So in this case, we could take the derivative of each one separately. If you leave it like this, the 4x is easy. The 2 over x squared, you could use the quotient rule. But because the numerator is a constant, it'll be a little easier if we just write it as 4x plus, and then if we move that up to the numerator, it'll be 2x to the negative 2. Again, it's not wrong to use the quotient rule there. It's just easier to just move it up here since the numerator is a constant, and then we can just use the power rule. So now let's go ahead and find the derivative, f prime of x. So the derivative of 4x is 4. And then we use the power rule. Negative 2 times 2, that's going to be negative 4. X to the negative 3. All right, so on this one, it's a little bit different in terms of how you simplify. You could factor out a 4 here, but we'll still be stuck with this x to the negative 3, and it's kind of weird to factor out an x here when this one doesn't appear to have any x's. So we can simplify in a little different way. This is another method other than factoring that sometimes is a little easier than factoring. So I'll leave this one 4, and then minus, this will be 4 over x cubed. But to make sure we get all the critical numbers here, this is just single prime there, we want it as a single fraction if there is any fraction, kind of like the one we had over here. Notice when you have a single fraction, then you can easily set the numerator equal to 0, denominator equal to 0, and get all the critical numbers. But we don't quite have that yet, because this one's a fraction, but this one's not. So all you have to do is get a common denominator. In this case, the common denominator would be x cubed. So if we just multiply the 4 by x cubed over x cubed, we'll get f prime of x equals 4x cubed over x cubed minus 4 over x cubed. And then we can combine them to be a single fraction. So we get 4x cubed minus 4 all over x cubed. And now we can factor the numerator. So you can take out a 4, and we'll be left with x cubed minus 1 divided by x cubed. Now in this case, there is a difference of perfect cube factoring we could use, but it actually is easier if we don't in this case. Because whenever you use perfect cube factoring, whether it's a sum or difference of perfect cubes, the trinomial you get when you factor it always just gives you imaginary answers. So we really don't need to worry about those anyway. So it's easier if you just focus on the real ones. So 4 will never equal 0. If you set x cubed minus 1 equal to 0, if you add the 1 over to the other side and then take the cube root of both sides, you get x equals 1. And if you set the x cubed equal to 0, take the cube root of both sides, you get x equals 0. So those are our two critical numbers. And we just have to put them on the number line. And label it, label it f prime of x. And we'll have 0 and 1. And 1 came from the numerator, so that makes the derivative 0. But 0 came from the denominator, that makes the derivative undefined. So now, when we test here we can test -1. And again, we're just testing, and probably the easiest form is the factored form here. So negative 1 cubed would be negative 1 minus 1. That's going to make the numerator negative. Negative 1 cubed, that makes the denominator negative. Negative divided by negative is positive. Here we could test 1/2. 1/2 cubed is 1/8 minus 1. That's a negative. 1/2 cubed on the denominator is positive. Negative divided by positive is negative. And here we could test 2. If you test 2, 2 cubed is 8 minus 1. That's positive. 2 cubed is positive. Positive divided by positive is positive. So what this shows us about f of x. Now here it does tell you increasing, decreasing, increasing, but we're not interested in that, so you don't have to write that down, even though you could. So 1, let's take a look at that case first. So 1 goes from negative to positive, so this is a relative, which is the same as a local minimum. Now this looks like a local maximum, and it might be, but the one thing we have to be careful of, undefined ones, can we plug it in the original function? Remember it said, assuming the function's continuous there. So all you have to do to see if the function's continuous there is see if you can plug it in the original function and get a y coordinate or not. So if you plug in 0 back in the original equation, see how it makes it undefined? 2 over 0. So it's not continuous. We'd have a vertical asymptote there. I'll just put it's a vertical asymptote. So because of that, it's not a relative min or relative max. Sometimes it is one, because sometimes it's not a vertical asymptote, sometimes it's a corner or a cusp, if you can plug it in the original one, in which case it would be, but in this case it's not. So then we just have to state the relative minimum, which is the same as a local minimum. So the way we can state it and justify it, we can say f has a local minimum at x equals 1. And then to justify it, what we have to use to justify it is what's happening with the first derivative. It's since f prime of x, okay, this changes from negative to positive at x equals 1. Sorry about that. Hopefully this pen lasts for the rest of the video here. All right. Now let's take a look at the next one here. So now let's take the derivative of this one. And this one, notice, overall, since they're multiplied together, we're going to have to use the product rule. So when we take the derivative here, g prime of x we'll take the derivative of the first one, which is 3x plus 1. The derivative of that is just 3 times the second one as it is, x minus 5 squared, and then plus the first one as it is, 3x plus 1, times the derivative of the second one. So they were using the power and chain rule, but it's a pretty simple chain rule. So when you bring down the 2, I think my pen ran out here, so let me just switch to writing on the, actually I'll just make a part 2 video of this here. So I'll pause it right here and then I'll let my pen recharge and make a second video on it. Sorry about that.